Hello, welcome to another module in this massive open online course. Alright, so we are looking at the autocorrelation function of the transmitted digital communication signal, that is expected value of xt into xt plus tau. So, we want to compute the autocorrelation function expected value of xt into xt plus tau. Now, substituting the value of xt, I have expected value of, well, xt is nothing but summation k equal to minus infinity to infinity a k pt minus kt times, well, xt plus tau. So, summation m equals minus infinity to infinity a m pt minus mt, close the brackets. Now, we expand the summation, that is expected value of, well, summation k equal to minus infinity to infinity summation m equal to minus infinity to infinity a k a m p, well, of course, this is x t plus tau. So, this has to be t plus tau minus m t. So, this is your x t, this whole thing, and this is your x t plus tau. So, p t of t minus k t into p t of t plus tau minus m t. Okay. Now, if I take the expectation operator inside, so if I take the expectation operator inside the summation, we have, taking the expectation operator inside, we have, well, summation k equal to minus infinity to infinity summation m equal to minus infinity to infinity expected value of a k into a m times p t minus k t times p t t plus tau minus m t. Now, if you can look at this quantity expected value of a k into a m, remember we already said the symbols are independent, identically distributed. Therefore, expected value of a k a m, if k is not equal to m, we have seen this expected value of a k a m, if k not equal to m is expected value, because symbols are independent, this is expected value of a k into expected value of a m, this is equal to 0. So, this is equal to 0, since symbols are, the digital symbols are IID, 0 mean. Since symbols are 0 mean IID, therefore, expected value of a k m 0, but if only if k is not equal to m, if k is equal to m, then it becomes expected value of a k square, and that is not equal to 0. So, only those terms will survive in this summation in which k is equal to m. all the other terms will vanish because expected value of AK times AM is 0. Okay. So, therefore, the summation equivalently reduces to expected value or summation k equal to. So, there is only now k equal to minus infinity to infinity, because only terms corresponding to k equal to m will survive. This will become expected value of AK square, right, into P, well, T minus KT into PT plus tau minus KT. Now, if you can look at this quantity expected value of AK square, that can be simplified as follows. We know that probability AK equal to A is half, we have assumed symbols are equiprobable. Probability AK equals minus A is also half. So, expected value of AK square equals half into A square plus half into minus A square. Both of these are A square, minus A square is also A square. So, half into A square plus half into A square, which is simply A square. So, this quantity expected value of AK square is simply A square, or we can also call this as PD, which is the power of the data symbols. This is PD. Okay, this is simply your data symbol. This is simply the power of the data symbols. Therefore, this reduces to PD times summation k equal to minus infinity to infinity PT T minus KT PT T plus tau minus KT. Okay. Now, if you can see this quantity here, okay, this is our autocorrelation function. Now, if you can see this quantity here, this quantity here depends on T. When we have expected value of xt plus xt into xt plus tau, we know that when expected value of xt into xt plus tau depends not only on tau, the time shift tau, but also depends on t, then the resulting random process is not wide sense stationary. Therefore, what we can see here is that this digital communication signal is not wide sense stationary. Since it depends on t, hence it is not wide sense stationary. That is basically wide sense . We would like to therefore convert this, right, because remember we wanted wide sense stationary signals are very helpful to us because they are suitable to be studied, alright, easy to be analyzed and characterized, and more importantly we can evaluate their power spectral density to characterize the spectral distribution of the power. So, we want to convert this signal, which is not wide sense stationary, this digital communication signal, into a wide sense stationary signal. Therefore, what I am going to do is I am going to do the following, is I am going to take my signal xt and I am going to move like a slight modification k equal to minus infinity to infinity AK PT minus KT, capital T, that is same as before, but I am also going to introduce this tau naught, which is a random delay. So, this quantity tau naught is a random delay of the signal, and this is uniformly distributed. We are going to assume this is uniformly distributed in 0 to that is basically a uniform distribution, or let us, so this is T naught, sorry, not tau naught, T naught, and it is uniformly distributed in 0 to T, and you can see a uniform distribution in 0 to T is given as follows. It is of height 1 over T. So, this is T, the distribution is 1 over T in 0 to T. So, this is your f of, well, f of T naught of T naught. This is the uniform probability density function of T naught. This is your uniform probability density function. Okay. So, now what we are assuming is that this digital communication signal has a random delay T naught, which is basically distributed in uniformly in 0 to capital T, where capital T is the symbol time, 1 over T is the 1 over capital T is the symbol rate. Okay. So, now we have, again let us go back to our expected value of x t into x t plus tau. This is going to be, well, the same thing. Let us start with P d summation k equal to minus infinity to infinity P t t minus k t. Now, in addition there is this delay T naught times P t t plus tau minus k t minus T naught. Okay. Now, I have to take the expected value of this, because T naught is random, I have to take the expected value average with respect to average or expected value with respect to average or the expected value with respect to T naught, and to take the average with respect to T naught, all I am going to do is I am going to multiply by the probability density function, that is, well, let me write the complete expression. I have to multiply with the probability density function of T naught, that is P t t minus k t minus T naught into P t t plus tau minus k t minus T naught into dt naught. So, multiply by the probability density function and integrate. So, this is basically averaging with respect to which is basically your random delay. This is your random delay. Now, f of T naught, that is the uniform probability density function. So, f of T naught equals 1 over T 0 less than T naught less than equal to T, it is 0 outside, that is in this interval 0 to capital T, it is 1 over capital T, 1 over the symbol time T, otherwise it is 0. Therefore, I can write this thing as follows. Therefore, I can write expected value of x t into x t plus tau is summation k equal to minus infinity to infinity integral 0 to t, well, 1 over t, f of t naught is 1 over t, 1 over t is a constant. So, I can bring that outside, 1 over t p t t minus k t minus T naught times P t t plus tau minus kt minus t naught into dt naught. Equals Pd over T summation k equal to minus infinity to infinity. Okay. Now, what I am going to do is I am going to employ a substitution here, that is, let us employ the substitution T naught plus, let us employ the substitution T naught plus kt equals T naught tilde. So, we have dt naught equals dt naught tilde, and this becomes, well, Pd over T times summation k equal to minus infinity to infinity, well, integral limits become, well, T naught plus kt equal to T naught tilde. So, limits become kt to k plus 1 t, T naught plus kt is T naught tilde. So, this is Pt minus T naught tilde into Pt plus tau minus T naught tilde into dt naught tilde. Now, if you can look at this integral, each integral is from kt to k plus 1 t, each integral is from kt to k plus 1 t, k is from infinity minus infinity to infinity. Therefore, the entire, this can be, so we have a sum of several integrals, each integral is going from kt to k plus 1 t, and k itself is going from minus infinity to infinity. Therefore, I can replace it by one integral going from minus infinity to plus infinity, that is the whole point. Okay. So, I get Pd over T integral, I can combine the summation and integral as minus infinity to infinity, well, Pt t minus T naught tilde into Pt, well, T plus tau minus T naught tilde into dt naught tilde. Okay. So, that is my resulting integral. Now, what I can do is I can further employ a substitution t plus tau minus T naught tilde equals T naught prime, which implies minus dt naught tilde equals dt naught prime. So, therefore, this integral further becomes Pd over T. Well, now you have to be careful, T plus tau minus T naught tilde, when T naught tilde is minus infinity, this becomes plus infinity. When T naught tilde is infinity, T naught prime becomes minus infinity times, well, P T minus T minus T naught tilde equals tau prime T naught prime minus tau into Pt T plus tau minus T naught tilde, that is T naught prime dt naught prime, or d minus T naught prime, because d T naught tilde minus d T naught tilde is d T naught prime. So, this becomes minus d T naught prime, and this minus reverses the order of integration. Okay. For integral you bring the minus sign outside, and integral from infinity to minus infinity becomes integral in minus infinity to infinity. So, therefore, we have something that is P d over capital T integral minus infinity to infinity P t T naught prime minus tau into P t, or let me write it the other way, P t into T naught prime. T naught prime is simply a dummy P t into T naught prime minus tau. Remember, T naught prime is simply a dummy variable, this is T naught prime. And now, if you look at this, you will observe something remarkable. If you look at this, you will observe this whole thing, now we have successfully avoided or successfully removed its dependence on t, which is the specific time instant. So, this does not depend on t, it only depends on tau. So, it does not depend on t. Only depends on tau. Hence, now x t is wide sense stationary. In fact, this is your expected value of x t into x t plus tau, which is basically your, you can call this as r x x of tau, depends only on tau. And in fact, you will observe something very interesting. If you look at this integral minus infinity to infinity p t t, let us write down this integral minus infinity to infinity p t minus or p t or p t naught. This is simply a dummy variable. So, this is t naught prime minus tau or p t naught prime into t naught prime minus tau if you remember, this is nothing but the autocorrelation of the pulse. This is r p t of tau. This function is indeed the autocorrelation function of the pulse p t of p t. Okay. So, this is the autocorrelation of the pulse p t. Autocorrelation of the pulse p t, and therefore, this is nothing but p d over t times the autocorrelation of the pulse p t, and therefore, we finally have a very elegant result for this, that is expected value of x t, that is r x x tau equals expected value of x t into x t plus tau, which is equal to p d over tau times simply, which is equal to p d over tau, which is simply equal to p d over t times the autocorrelation function p t t tau of the pulse, and this is a very interesting result. Okay. So, what we have seen is that the autocorrelation of this thing is indeed related to the pulse, and it depends on the autocorrelation of the pulse, it depends on the. So, what we are able to see is something very interesting, autocorrelation of the signal depends on autocorrelation function of the pulse Pt of t. It depends on the autocorrelation function of the pulse Pt of t. In fact, if you now take the Fourier transform of this autocorrelation function, okay, so we have Rxx tau equals Pd over t, Pd over t is a constant times R Pt of tau, okay, it depends on the autocorrelation of the pulse. If you take the Fourier transform of this, you will get the power spectral density, that is you will get Sxx of f, which is equal to Pd over t times the Fourier transform of the pulse, which is nothing but S Pt of f. This is nothing but the autocorrelation, this is nothing but the energy spectral density of the pulse. Remember, if you take the Fourier transform of the autocorrelation function of a deterministic signal such as this pulse, you will get the energy spectral density. For a random signal, it gives the power spectral density. For the for a deterministic signal, the Fourier transform of the autocorrelation is the energy spectral, it is the energy spectral density, and we have this very beautiful relation where the Fourier transform of the pulse, that is we have the power spectral density of the transmitted signal, the PSD or power spectral density of the transmitted signal, that is xt. Okay. So, what we have able to show that the autocorrelation function, that is first we have converted this signal into a Whiteson stationary signal, and then we have been able to derive the expression for the autocorrelation. We have seen that as a very elegant expression. The autocorrelation function of the digital communication signal simply depends on the autocorrelation function of the pulse, and moreover the power spectral density of the transmitted signal is simply therefore proportional to the energy spectral density of the pulse, which is nothing but the Fourier transform of the autocorrelation function of the pulse, and that is a very interesting result. Okay. So, we have been able to derive now the power spectral density of the signal, which gives the distribution of the spectral distribution of the power of the transmitted digital communication signal. Okay. So, we will stop here and look at this further in the subsequent modules. Thank you very much.